Hello viewers and welcome to the e-learning classroom. So today we want to look at the KCSE 2024 Physics Paper 1. So we'll go straight to the questions. So we start with the first question. Figure 1 shows the vernier scale of a vernier caliper. So we have the diagram here. And then the question on the figure, include the main scale so that the vernier caliper shows a reading of 3.15 centimeters. So we have the vernier scale and we are supposed to insert the main scale so that we have a reading of 3.15 centimeters. So we'll start with 3.1, which is the point before the 0 mark of the vernier scale. So before 0, we start with 3.1, and then the fifth mark should coincide. So when we have 3.15, 3.1 is the mark before the 0 mark, and then the fifth mark of the vernier scale should coincide. So that is what we have there if you check the diagram. Let's go to the second question. Explain why weight of an object is a vector quantity. Explain why weight of an object is a vector quantity. Weight of an object depends on the pull of gravity, which is directed towards the center of the earth, hence is a vector quantity. So definitely we are simply talking about the pull of gravity, which now has a direction towards the planet, definitely towards the center of the planet. So and weight depending on the pull of gravity simply will have the same direction. So that is simply means that weight is a vector quantity. We go to the third question. Figure 2 shows the shape of a bimetallic strip made of metals A and B when heated. We have the bimetallic strip with two metals A and B. State the reason why the strip appears as shown. State the reason why the strip appears as shown. Metal A expands at a faster rate than B, forcing the bimetallic strip to bend. So in other words, you can also say that metal A has a higher expansivity than metal B, hence causing the bending. So simply we are comparing the rates of expansion, and we are now saying that metal A has a higher rate of thermal expansion. Let's go to question 4. It is observed that in order to balance a seesaw, the heavier child sits closer to the pivot. It is observed that in order to balance a seesaw, the heavier child sits closer to the pivot. State the reason for this observation. So since the moment of force is given by product of force and the perpendicular distance from the pivot, the heavier child sits closer to the pivot in order to reduce his or her moment of force, hence balancing the lighter child. So basically this question is testing on the factors affecting the moment of force or the turning effect of force, and we know since moment of force is a product of force times distance, then simply if the child is heavier, then the distance has to reduce. We go to question 5. Explain one way in which a person maintains stability when carrying a bucket of water in one hand. Explain one way in which a person maintains stability when carrying a bucket of water in one hand. By leaning on the opposite side or raising the hand on the opposite side of the bucket. So simply we are saying that you can balance by either bending on the other side, of course you can lift the hand which is in the other side of the bucket. We go to question 6. Figure 3 shows a simple hand sanitizer dispenser. So you can see the sanitizer. We have the piston, we have the nozzle, we have the vent, we have the sanitizer itself, and then the question is explain how it works. Remember, this one is an application of Bernoulli's effect, so we simply need to understand how Bernoulli's effects work. So when the piston is moved in once, the air above the tube moves at a higher velocity, hence the air pressure above the tube reduces through Bernoulli's effect. When the let me repeat that again. When the piston is moved inwards, the air above the tube moves at a higher velocity, hence the air pressure above the tube reduces through the Bernoulli's effect. The greater atmospheric pressure outside the vent forces the liquid to rise through the tube. The liquid mixes with the air above the tube and is sprayed out. So what we are saying simply is that when the air is moving out, at the point where the tube is narrowing down, the pump is narrowing, then simply due to the principle of the continuity of the liquid, you realize that for a liquid that is moving, the fluid flow must be constant. And that simply means that the air will have a higher velocity above the tube because of the narrowing down of the vent, of the part approaching the nozzle, and that simply means that the pressure will decrease. And we know in Bernoulli's principle and effect, when the air moves at a higher velocity, then the pressure decreases, and that is simply to say that the air pressure above the tube or nearer the nozzle will decrease, and that simply means that the atmospheric pressure, which is now greater through the vent, now forces this liquid to rise through the tube, just like the working of a drinking straw or maybe a sledge. And then when the piston is pulled outwards, the air pressure in the pump reduces, and the greater atmospheric pressure outside forces the air to get in through the nozzle. So what you are saying is that when you are pulling outwards now the piston, you realize that the air inside the pump will now expand, and that simply means pressure decreases. And when pressure decreases, then the atmospheric pressure, which is now greater, will force the air to get in through the nozzle. Let's go to the next question. Figure 4 shows a marble that was set into oscillations when released in a ball. So we have the marble there, we have the ball. On the axis provided, sketch the velocity time graph for the motion of the marble in one complete oscillation. So when we have this marble here, you realize that as the marble moves down, it accelerates, but as it rises on the other side, it now decelerates, and then it will go back as it accelerates again, but now in the opposite direction, and then also decelerate in the opposite direction. So that simply means the graph is as shown. We have the graph whereby now velocity is increasing to maximum, then decreasing to 0, and then increasing in the opposite direction to maximum again, and then decreasing to 0 again. Question 8. State the meaning of the term viscosity as used in fluids. Viscosity refers to the friction or resistance to motion in fluids. Viscosity refers to the friction or resistance to motion in fluids. Let's go to question 9. A machine raises a mass of 20 kg through a distance of 0.2 meters when an effort of 100 Newton is moved through a distance of 0.32 meters. Determine the velocity ratio of the machine. So we are given the mass, and also we have the distance of the effort and the load, and then we are trying to find the velocity ratio. So we know velocity ratio is given by effort distance divided by the load distance. So that is simply to mean 0.32 meters divided by 0.2 meters, which gives you 1.6. Then question 10. A gas bubble is released at the bottom of a pot containing water. It is observed that as the bubble rises to the water surface, it expands. Explain this observation. As the bubble rises from the water surface, we are told it is expanding as it rises. So that is simply the Boyle's law. As the bubble rises, the pressure due to the liquid column above the bubble reduces. Hence, the volume increases through the Boyle's law. So that is simply to state that, volume and pressure, the pressure and volume, as per the Boyle's law, they are inversely proportional. Let's go to question 11. A stone of mass 200 gram is tied at the end of a string 1 meter long, is whirled in a horizontal circle at an angular velocity of 10 radians per second. Determine the centripetal force acting on the stone. So we have a stone of mass 200 gram, the length of the string 1 meter. The length of the string is also the radius of that oscillation, and then we are told it is whirled at a angular velocity of 10 radians per second. So we have the mass, radius, and also the angular velocity. We are told to determine the centripetal force. So we know the basic formula: centripetal force is given by mv squared over r. But now, because we don't have the v, which is the linear velocity, v equals omega r. So we replace v squared with omega r squared. So we get the values there, because we have mass 0.2 kilogram, angular velocity is 10, radius is 1 squared, and then we are dividing by radius again. So the answer becomes 20 Newton. We go to question 12. An object is released into a Eureka can full of water. It is observed that the weight of the displaced water is equal to the weight of the object. Explain this observation. So this is now the law of flotation. So we are told the weight of the object is equal to the weight of the displaced water. So the right answer there, this implies that the object is floating in water, hence it displaces its own weight, or it displaces weight of water equal to its own weight as per the law of flotation. Let's go to question 13. A student observed that smoke particles in a smoke cell moved randomly. A student observed that smoke particles in a smoke cell moved randomly. State what A causes this motion. What causes this motion in a smoke cell experiment? So the smoke particles are being bombarded by the invisible air molecules, which are in constant random motion. We go to part B. Explain part B. Explain what happens to the motion of the particles if the temperature in the cell is increased. What happens when the temperature is increased? So the smoke particles will be seen moving faster, since increase in temperature increases the kinetic energy of the air molecules, making them move faster and colliding more with the smoke particles. Definitely, increase in temperature increases the kinetic energy of the particles, and that is simply to say that when the kinetic energy increases, then the particles will also move faster, and they will therefore collide more with the smoke particles. So let's go now to section B. So question 14A, Roman 1, state the meaning of the term relative density. Say the meaning of the term relative density. Relative density is the ratio of density of a substance to the density of water. In other words, you can also see that relative density is the number of times a substance is denser than water. The number of times a substance is denser than water. We go to Roman 2. State two areas of applications of relative density in daily life. Two areas of applications of relative density in daily life. So we have in electricity to check the state of charge of a lead acid accumulator. In other words, when we want to know whether a lead acid battery is full, we simply use an hydrometer to check the relative density of the acid, and that is one of the major applications. Then we have to test the purity of a substance, e.g. the milk. maybe in dairy farm, when we want to check whether the milk is pure, we still use the hydrometer. So we are talking about the same thing. And then used in geology to determine the mineral content. Those are some of the applications of relative density in real life. Let's go to part B. A student blew air into a balloon, tied it up, and released it into the air. It floated for some time, but slowly descended to the ground and settled. Explain why the balloon settled on the ground. So this balloon is filled with air, and then it rises. It first floats for some time and then descends and settles, and then we are trying to explain why it is settling. So when it settles, it simply means that when the balloon floated, the balloon floated when the upthrust acting on it is equal to the weight. In other words, the upward force is equal to the downward force. That is, the upthrust acting on the liquid is equal to the weight of the balloon together with its content. And then after some time, the balloon cooled. In other words, the air that was inflated cooled and contracted, hence the upthrust acting on it reduced and became less than the weight of the balloon and its contents, hence the balloon settled on the ground. So what we are simply saying here is that when the balloon had expanded, initially the upthrust and the weight of that balloon, they are all equal. In other words, the downward force and the upward force are equal. But after some time now, this air that was blew inside the balloon cooled, and the balloon now decreased the volume. Upthrust is given by rho Vg. So one of the factors affecting upthrust is volume. So when the balloon decreased in volume by contracting, then simply means that it will go down, because now the upthrust reduces and now weight becomes greater. Let's go to the second part. State 2 ways in which the balloon could be made to keep floating in the air. 2 ways of making the balloon keep floating. So number 1, by filling the balloon with a gas which is significantly less dense than air. That is one of the ways, by filling the balloon with a gas which is significantly less dense than air. Number 2, by increasing the volume of the balloon or through heating or warming air inside it, leading to an increase in the upthrust force. That's another way you can do that. By cooling the air surrounding the balloon, leading to an increase in its density, hence increase in upthrust force. So you can also decide to cool the air, and that simply means that the balloon will now contract, and when it contracts now, when you are cooling the air around the balloon, simply means that the density of that air will increase. And when the density of the density of air surrounding the balloon increases, it will also increase the upthrust, and that means the balloon will be kept floating. Let's go to number C. A hollow metallic cube of volume 1000 centimeter cubed is submerged in a liquid of density 1100 kg per meter cubed. Determine the upthrust acting on it. So we have the volume, we are also given the density, we also given the pull of gravity, and then we are trying to determine the upthrust. So upthrust is given by rho Vg, so we just replace the values but in SI units. So density is 1100, volume in SI unit is 0.0001 meters cubed, and G is 10. Then when you multiply them, you get 11 Newton. Let's go now to question 15a. During an experiment to verify a certain law, a student was provided with some masses, a spring and a meter rule. State the law the student wanted to verify. So we have some masses, we have a spring, and we have a meter rule, and we are now verifying some law. So we are trying to determine the law we want to verify. So of course, having a spring, we are simply verifying the Hooke's law. Then Roman 2, state one other apparatus the student needed in order to carry out the experiment. So the other thing we needed is the stand, of course, or the clamp stand, or the Bose clamp stand. Then Roman 3, explain how the measurements taken during the experiment are used to verify the law in part A, in part Roman 1 above. So suspend, so how we can verify Hooke's law applying those values. So the first thing is suspend the spring on the stand and record its length. So you first suspend that spring and you record the length of that spring before anything, before adding the mass, and then add masses one by one as you record the extension. So you'll add the first mass, of course the spring will extend, you record that extension, second mass, third mass, fourth mass, as you are recording the extensions for each one of them, and then you plot a graph of force against the extension. So, and when you're plotting the graph, you'll also explain how the graph looks like. So the graph is a straight line with a positive gradient and passing through the origin. The graph is a straight line with a positive gradient passing through the origin, which shows that the force is directly proportional to the extension, provided that the elastic limit is not exceeded. It shows that the force is directly proportional to the extension, provided that elastic limit is not exceeded. So we have question B. A load of 0.04 Newton causes an extension of 0.4 centimeters on a certain spring. Determine the load that will cause an extension of 0.6 centimeters on the same spring. So we first need to get the spring constant, and the spring constant is given by force all over extension. So you have the force 0.04 divided by the extension, which is 0.04 meters, and then when we divide, we get the spring constant 10 Newton per meter. So once we have the spring constant, then we know that spring constant, the force is given by Ke. So we have the force, which is we are looking for, and then the constant is 10. Extension for the new one is 0.06 meters, so which gives us the force which you are looking for, 0.06 Newton. Number C, a student was provided with a piece of wire and has to make a spring. After coiling the wire on a rod, the spring appeared as shown in figure 5. So we have this new spring here made from a wire that has been coiled through a rod, and then we are told state 2 ways in which the student can modify the spring to make it stiffer. 2 ways you can the student can modify the spring to make it stiffer. So number 1, using less number of turns per unit length, reducing the diameter of the spring, using a thicker wire to make the spring, or using a shorter spring. And then we go to question 16. A, figure 6 shows a setup that may be used to determine the acceleration due to gravity. Figure 6 shows a setup that may be used to determine the acceleration due to gravity. So we have the ticker timer, we have the tape, we have the ball, and then we have the floor. Describe how the setup may be used to determine the acceleration due to gravity. How the setup may be used to determine the acceleration due to gravity. So number 1, switch on the ticker timer and release the ball to fall freely. So you release that ball to fall freely while the ticker time is on. Get the time between the dots from the frequency of the ticker timer. You remember the dots made by a ticker timer, so you'll get the time between the dots, and the time will be, of course, 1 over frequency. Then determine the initial and the final velocities. You can the normal way we determine using the ticker timer, and then determine the acceleration due to gravity using the formula. Acceleration is final velocity minus the initial velocity divided by the time. That is a normal way we determine the acceleration, but of course this one will be due to gravity since the ball is accelerated by the gravity. Let's go to part B. A stone of mass 0.02 kilogram tied at one end of a spring is whirled in a vertical circle of radius 1 meter. Determine the minimum velocity required for the stone to maintain a circular motion. So we have this stone that is whirled in a vertical circle, and then we are trying to find the critical velocity. So we know for the critical velocity, tension must be 0. That is at the top, and then that is to imply that centripetal force is equal to the weight of the stone. And of course, now you can cancel the masses, then you are left with critical velocity is equals to square root of rg. We have the radius and the gravity, so you get the critical velocity is 3.162 meters per second. State 2 applications of centripetal force. Applications of the centripetal force: we have the merry-go-round, washing machines, we have the string, we have centrifuges, we have speed governors in operation. Those are all the applications of centripetal force, and there are many more. Then you can check on each one of them actually to see how they work. Let's go to question 17, number A. It is observed that when salt is sprinkled onto the surface of ice, the ice melts. It is observed that when salt is sprinkled on the surface of ice, the ice melts. Explain this observation. Salt is an impurity which lowers the melting point of ice. So that is simply factors affecting the melting point. And of course, now because we are dealing with the salt, how impurity affects the melting point. So we know impurities normally decrease. The presence of impurity normally decreases the melting point, and that is what happens, that this ice will now melt at a lower temperature. Number B, state two factors that determine the pressure exerted by solids. Factors affecting pressure in solid, we have the weight of the solid, also the force applied. Then we have the area in contact. We know pressure is force over area, so that is to imply that the factors affecting, you have the area, the area in contact, and also the force applied. We go to number C. A person mixed 2 kg of hot water at 70 degrees Celsius with 3 kg of cold water at 22 degrees Celsius for bathing. Given that the specific heat capacity of water is 4200 joule per kilogram per Kelvin, determine the final temperature of the mixture, assuming there was no heat loss. So we are given this person is mixing the hot water and the cold water for bathing, and then we are told to determine the final temperature. So we know heat lost is equals to heat gained. In other words, heat lost by the hot water equals heat gained by the cold water. Of course, for the hot water, we have the mass, we have the specific heat capacity, change in temperature, and also for the cold water, so we just replace the values. We don't have the final temperature only, so that is the one we are looking for. So you'll find that the final temperature is 41.2 degrees Celsius. And it's also important you know that when you're looking for change in temperature, for the one that is losing heat, you take the larger temperature, which is initial minus final. But when you go to the heat gained side, you take the final minus the initial, because the final temperature is bigger than the initial. So that is something you need to check. Roman 2, state two possible factors that lead to heat loss in one above. So the factors leading to heat loss: 1, we have heat absorbed by the container, heat lost through evaporation, radiation of heat through the container. The container surface, of course, absorbs some heat and also emits through radiation. Then we also have the evaporation, which leads to cooling, as well as heat absorbed by the container itself. Then we have question D. Some water at 60 degrees Celsius was heated until it started to boil after t seconds. We are heating water at 60 until it boils. Then Roman 1, on the axis provided, sketch a graph of temperature. Again, it's time for the water till it boiled. You're looking for the graph of water until it boiled from 60, so that is the starting point. So of course now the temperature rise from 60 all the way to 100, and then it will remain constant because that's the boiling point of pure water. So that's why the graph is having that shape. So and then explain the shape of the graph. So temperature of the water rises until it reaches the boiling point, where it remains constant until the water has vaporized. So that is a basic graph for heating. We go to the last question, number 18A. Explain why the walls of a dam are thicker at the bottom than at the top. Why the walls of the dam are thicker at the bottom than at the top. Since the pressure in liquids increases with the depth, the pressure of water at the bottom is much larger than at the top. Hence, the walls are thicker at the bottom to increase the area in contact, hence reducing the liquid pressure. So simply we are looking at the factors affecting the pressure in liquids, and now specifically because we are dealing with the top and the bottom, that is the depth, how depth affects the pressure. And now we are saying because now at the bottom the pressure of the liquid is higher, that is one of the shape of the wall is a bit slanted. or is thicker, so that now it can increase the area in contact in order to minimize that pressure, or in order to be able to overcome that pressure, because otherwise the wall could collapse. Let's go to number B. Figure 7 shows a simple hydraulic lift system. We have the lift system there. We have piston 1, area 1, piston 2 and area 2. Then we are told, given that the areas A1 and A2 are 0.2 meters and 4 meters squared respectively, determine the maximum load that can be lifted at piston 2 when a force of 200 Newton is applied to 1. So we have that setup. We all know that this is an application of Pascal's principle, so whereby pressure applied at one side must be the same pressure that is transmitted to the other side. So we all know that when you are applying Pascal's principle, the pressure applied at one point will simply be the same pressure transmitted to the other side. So the formula applied here is force 1 all over area 1 is equals to force 2 all over area 2. So the force 1 is 200 Newton. We have area 1, which is 0.2 square meters. Then force 2 we don't have. Then area 2 is 4, so which gives us the force 2, which is also the load that can be lifted, as 4,000 Newton. Roman 2, state 2 reasons why water is not suitable liquid for use in this system, why we cannot use water. In other words, what are the properties of a liquid that can be used in hydraulic systems? So water vaporizes easily, that's why it cannot be used. Another reason, water has a relatively higher freezing point. That is to mean that water will easily freeze, because the freezing point is simply 0 for pure water, so it will easily freeze if temperature reaches that point. Water has a relatively lower boiling point. That's another reason. It boils very fast, maybe at 100 degrees, so that is why now we cannot use the water there. In other words, the liquid used for that purpose must have a wide temperature range, which the water does not qualify. C, figure 8 shows a pair of scissors. So we have the load, we have the fulcrum. We are told to label, simply to label the load, fulcrum and effort, which we have labeled as shown. We have the fulcrum of the pivot, we have the load there, of course, and also the effort where the force is applied. And then the next question is, explain how the velocity ratio of the pair of scissors may be reduced. How to reduce the velocity ratio of this? By increasing the load arm. We know V dot R, or velocity ratio, is given by effort arm over load arm. So that means if you increase the effort arm, then if you increase the load arm, if you increase the load arm, because effort arm over load arm is in the denominator, so they are inversely proportional. So if you increase the load arm, the velocity ratio will decrease. Another way is by reducing the effort arm. We have said V dot R is effort arm over load arm. So effort arm is in the numerator. So that means if you decrease the effort arm, you'll also decrease the velocity ratio. Then the last question, state the reason why it is important to minimize the velocity ratio. Why should you minimize the velocity ratio? So this one is to increase the efficiency of the system. To increase the efficiency of the system. You all know that efficiency is given by mechanical advantage of a velocity ratio multiplied by 100%. So that is why now we are saying you have to decrease this one. You have to decrease the velocity ratio in order to increase the efficiency, or to make the machine more efficient in working. So that is those were the questions for last year's paper 1, the KCSE, so 2024. So, and those are some of the responses that were expected. So it's important to look at those questions and also carefully analyze some of the key areas in each question, because you realize that some of the questions have a technical areas whereby now you might think the answer should be written in a certain way, but when you look at it critically, you realize that there is a way you need to write the answer. So it's important as you look at the paper, you just look at the key areas that were tested, and also how the responses should be given, by maybe identifying the key keyword in each question. So that makes the end of paper 1 2024 KCSE revision. And I want to remind you to subscribe and also stay tuned for more episodes, and also remember to like and share the video. Wish you all the best.